So, hi everyone, I am Shubhankar, and I'm going to present our work on differentially private data generation with missing data. We have been talking a lot about synthetic data in this workshop, and this is a problem that I've been looking at for a while now, and this is still in, we are still working on it, and any questions, criticism, comments are welcome. This is in collaboration with my supervisor, Professor Shi, and Professor Florian from the University of Waterloo. So this is I'll show you the problem statement that we have. So we have a private data set which lies beyond a privacy firewall. And what we want to do is we want to create a synthetic data set with an end-to-end budget of epsilon f delta f. We are using approximate DP here, but you can think of any, it's all fine. And we want to preserve like some utility guarantees of this synthetic data set, like downstream ML tasks or preserving the KV marginals on this synthetic data set. Why do you want to do something like this? Because there could be we could publish this data set in public, and someone can query this and get free answers, and they don't have to spend privacy budget. It's like already privatized basically. The benefits are like there's no limit on the number of queries after doing this, and you can ask non-complex, like non-DP queries, and the domain expertise isn't required for like when this is already public. And more specifically, we want to look into this problem today, that what if there are missing values in this private data set? Yeah, so moving ahead, when do we see such missing data? One could be human errors. There you could do like queries, like you have a survey and people didn't fill up some of the boxes in your survey, or due to privacy regulation, someone might have the right to forget and you have missing values in your data set. Or in case of a medical data set, there could be rare conditions due to which, some people don't have it, so it's like missing value for that particular rare condition. So these are some of the data generation methods, synthetic data generation methods that we are looking into. One of them, we are looking into statistical approaches, more in particular prive-based, where prive-based, we have talked about this yesterday as well, where prive-based basically works by training a Bayesian model. You learn the relationship between attributes. So let's say we learned that A and B are well correlated, C and D are independent columns. We compute the marginals for these well correlated or whatever we learned from the Bayesian model, and we sample from that noisy distribution to get our synthetic data set. The second type of approaches could be GAN-based approaches. We have a couple of approaches that we're looking into: PATI GAN, DPCT GAN. These are conditional GANs which work better for categorical data, and these basically work by generating by training a GAN network. You train this GAN using like DPSGD, let's say, and you basically throw off your discriminator, and the generator can then be used to generate synthetic data. And the third type of approach that we're looking into is some kind of mixed approach, in particular Camino, where we what it basically does is that it finds a sequence in the schema of the table. It goes column by column. So first you generate the first column A IID from its distribution in the data set, and then you keep generating the next column by learning the relationship between the previous columns and this particular column in a sequence. One common thing that we notice about all these mechanisms is that in the case of missing data, when you have, let's say you discard all the rows which have missing data, the utility of all these approaches kind of go down. So you do not want to disregard the rows which have missing values, right? So complete analysis, complete row analysis is bad for all these mechanisms. Okay, so on that end, we look into imputation of private data, and it can be done using multiple approaches. Some common approaches are statistical approaches like mean, median, mode imputation. deck imputation, hot deck, cold deck, and ML techniques like clustering, regression, classification. These are some, like it's an example of how these things work. In a mean imputation, we just take the column, we find the mean, and we fill up those red missing values there. We can similar do median or mode, and hot deck basically works by finding similar values in the data set, and cold deck works by getting the same information from a proxy data set. ML techniques can also be used for the same. Now we will look into the privacy cost of this imputation. So this can be done in two ways. One way is by splitting the privacy budget. You get like epsilon1 for the imputation and epsilon2 for generating the data set. However, we are not looking into this because we don't like it. It gives us another question like where should be split? What should be the percentage of imputation? What should be the privacy budget of the algorithm? So we look into the privacy cost in a different way. Here, let's say we have a data set, two neighboring data sets, D and D prime. The red values are missing, and the differing row is the green one here. So 25 becomes 22. And now if you do mean impute, you get these transformed data sets. For the D data set, the mean was 16. For D prime, because the neighboring data set now changes from 25 to 22, your mean value goes down to 15. So we can see that now TD and TD prime, they don't differ by one row, but they differ by 3 rows. 2 rows which were missing and the row which was the differing row. Now, in the worst case, this could be an order of n. So studying this from a kind of a stability kind of perspective of DP, in an end-to-end process, this could be like, this could cost you up to n, the whole process can be of n epsilon. So to this end, we look into what we call adaptive recourse methods, and we extend some of the previous the algorithms that we talked about earlier. So one of this is what we call prive-based enhanced. In prive-based enhanced, let's say you have these black values as missing values. You can instead learn on only the available rows, available data. So you don't have to disregard the complete 2 middle rows here. You can use whatever is available to get the distribution. And the second approach that we find an adaptive method for is the Camino method, where we can use this intermediate model not only to train, to generate synthetic data, but also to impute this missing values. So let's say this intermediate model is used to impute this black missing value here. This can be later used to use in the while generating the D column. So yeah, now these are some results that we have. This is on the adult data set, and we are looking into different kinds of missingness, like MCAR, missing completely at random, different kinds of missingness on the adult data set for 10%, 20% missing data. And here are the values for the marginal distance between this generated synthetic data and the original data. So smaller values are better. And the bold values here refer to the values that we get by only computing the complete rows, and the red values are after, like, with adaptive methods. So some inferences that we make from here are that GAN approaches are really, really bad. So they are really high. That's bad. And prive-based kind of performs well with complete rows, and Camino impute works better with its adaptive method. When we add the adaptive methods, Camino impute is better than prive-based enhanced for this one-way marginal task. And this is the second metric that we look into. It's the F1 accuracy. It's kind of like the testing accuracy that you get when you are training on the synthetic data. Here also we see that the GAN approaches perform really bad because they are only training on the complete rows. We haven't found any adaptive methods for them. And prive-based enhanced is a better better approach if you are going for this F1 metric. Yeah, so in conclusion, we studied DP synthetic data generation in the presence of missing data. We found out that classic imputation methods like mean imputation don't really work well, and then can be costly in practice if you're looking into this in an end-to-end privacy cost kind of metric. And there's no clear winning approach. Like for marginals, we found out that continuum impute is better. For F1 score, we found out prive-based enhanced is better. And these adaptive methods can be beneficial and can match to the no missing baseline. And these are some of the next steps that we are looking into. We want to find like the correlation between these missing types. I kind of skipped that in my slides. Like we have different kinds of missingness, missing completely at random, missing at random, and we want to see like which algorithm performs better at which missingness. And we want to figure out why GAN approaches perform so poorly. Is it only because of the task, or we didn't do a lot of hyperparameter tuning, maybe because of that? And we want to find like smarter GAN approaches for this kind of tabular data. And we also want to find like adaptive methods if there are any for these GANs. That's all from me. Thank you.